Hello friends, welcome to the another segment of chemical reaction engineering in the polymeric system. Here we are going to discuss about the condensation, that is the step growth polymerization under the edge of polymer process engineering. Now the topic which we have covered previously, we discussed about the chemical kinetics, we discussed about the reaction rates, we discussed about the rate law, examples, molecularity, order of the reaction, temperature reaction rate, collision theory, transition state theory, all those things we discussed a lot. Now, in this particular segment, we are going to discuss about the polymerization, step growth versus the chain growth reactions. Then step growth polymerization, we are going to discuss with the various properties of the step growth. Then we will discuss about the kinetics of step growth polymerization. And apart from this, the self-catalyzed step growth. Then we will discuss about the gel point and the molecular weight distribution. As we know that molecular weight distribution play a very vital role in deciding the properties of the polymer. Now, let us have a brief overview about the polymerization. Now, polymerization is the process which very small molecules, they are called the monomer, they combine chemically with each other to produce a very large chain like molecules, they are called the polymers. So, polymer is composed of the chains composed of the various monomers. Now, based on the reaction of all those monomers or all those monomer and polymeric chains, then there is a basic classification of the polymers. So, polymers are basically classified as addition or condensation polymers depending upon the type of polymerization reactions they involved in their synthesis. In this particular class of classification, this reflects the structure of starting monomers. Probably the most general classification scheme is based on the polymerization mechanism. This involved in the polymer synthesis. So, under this classification, the polymerization process, they are classified like step growth reaction or step growth polymerization, that is called the condensation polymerization, and the chain growth polymerization or the chain reaction polymerization, which is called as the addition polymerization. Now, here is a comparison between the step growth and the chain reaction. In the reaction mechanism, in the step growth, one reaction is responsible for the polymer formation, whereas in the chain reaction, the initiation, propagation and the termination, this reaction, they have the different rates and the mechanism. Then if we talk about the polymer growth, so any two molecule or any two molecular species present, this can react slowly or randomly and then the growth take place. In the chain growth, the growth reaction takes place by the addition of one unit at a time to the active end of the polymer chain. And if we talk about the polymer molecular weight, in step growth, molecular weight rises steadily. High conversion requires the high molecular weight. And in the chain growth, the high molecular weight polymer is formed immediately. If we talk about the monomer concentration, so monomer disappears in early stages of the polymerization, so that the say like P1 is the monomer, then P1 may react with the P1, it gives to P2 and this takes the disappearance, and then P2 may react with P1 to form the P3 likewise. In chain reaction, the monomer concentration decreases steadily throughout the reaction. Now, if we talk about the composition in step growth polymerization, the molecular species of any length, referred as oligomers, exist throughout the reaction with the length distribution broadening and the shifting to higher molecular weight with increasing reaction time. Whereas in the chain reaction, the mixture contains primarily the monomers and polymers and only small amount of growing polymer chains. Now, let us talk about the condensation polymerization. Now, physically, the condensation is a process in which a gas phase changes to a liquid phase under the certain conditions, that is the temperature and pressure, and these phenomena can be seen in nature many times. In chemical reaction, on the other hand, the condensation is a process which two monomers react to form a larger molecule and eliminates a smaller molecule, sometimes water, ammonia, methanol or hydrogen chloride. As an example of the reaction of the two monofunctional compounds, N-hexylamine and hexanic acid. This gives amide of molecular weight of 199. Let us take this monofunctional molecules. Here CH3 and 2, this is amine, then H, the acid, this gives the amide, and this water is being eliminated. Now, the same reaction can produce the polymer if reactant have two functional groups. These are the two functional groups. For example, the polymers they prepared for the condensation reaction are Kevlar, nylon, terylene, etc. Now, in this type of like if we talk about the step growth in detail, that in this type of polymerization methods, monomer with di or multifunction groups, they are necessarily at least to form a polymer. Now, a difunctional monomer or equal molar amount of two different difunctional monomer, this can be formed a linear high molecular weight polymer. Now, in a step growth polymerization, the molecular weight of polymer chain, they build up slowly, and there is only one reaction mechanism for the formation of polymer. Now, the polymerization reaction proceeds by an individual reaction or of the functional group. Obviously, when we need to proceed for the polymerization reaction, there must be some functional group. Now, for the two monomers, they react to form a dimer. Like here, P1 and P2, they form the P2, and this is the reaction product. And the dimer may now react with either dimer or dimer monomer, or sometimes if the trimer is formed, then it can react with the trimer. So, monomer plus dimer, they form the trimer, and dimer plus dimer, they form the tetramer likewise, and these can react all together. Now, this process continues and each reaction of a functional group proceeding essentially at the same reaction rate until over a relatively long period of time, a high molecular weight polymer is obtained. Now, here you see this is a systematic illustration of a fundamental difference in the reaction mechanism. Here you see that dimers are formed in the chain reaction, it is quite different. Similarly, the trimer, tetramer, and all these things are formed. Now, let us talk about the monofunctional versus difunctional condensation polymerization. The monofunctional condensation reaction, in this type of a reaction, making an ester requires a carboxylic acid, an alcohol, and acid catalyst. So, you see that here this is the reaction mechanism. Now, difunctional condensation polymerization, if we start with the diol, that is a molecule with the two alcohol groups, instead of a normal alcohol which we used previously, they reacted with the dicarboxylic acid, and therefore the esterification can happen at either end of the molecule forming a long molecule containing the multiple ester linkage. You see over here that this is a dicarboxylic acid reacts with the dialcohol and it gives the polyester. This is the structural unit. Now, let us talk about the monofunctional versus difunctional condensation polymerization. The formation of the polyester, polyamide, or a polyurethane represent the typical condensation polymerization. Now, these reactions can be written as like polyester, this is for the polyamide, and this is for the polyurethane. And you see that this is the broad spectrum of this particular representation. Let us talk about the step growth polymerization. Step growth polymerization is a stepwise reaction between a bifunctional or a multifunctional monomers, which results in the formation of high molecular weight after extensive number of steps. So, all molecules are reactive, hence most monomers have a short chain, that is called the oligomers in early stages, and these chains may combine over the period of time to form a longer chain. Now, type of polymer this form depends upon the functional group in the monomeric unit. The step growth polymerization usually that involves the small byproduct molecule formation, and that is called the condensation polymerization. Now, let us talk about the linear step polymerization or linear step growth polymerization. This falls into two categories, A-B type of polymerization. Now, each monomeric unit has two types of functional group. Each consumed monomer unit corresponds to a repeat unit along the polymer chain. Let us take this particular example. Now, AA and BB type of polymerization. Each bifunctional monomer has similar functional groups and each repeat unit arises from two monomer molecules. For example, let us consider the esterification of ethylene glycol and terephthalic acid to produce the PET. Now, this is the example. Uh, there are several polymers which are commercially important. So, the commercially important polymer, they produces AA and AB type of polymerization or a polymers. This includes the aliphatic polyamides like nylon 66, which is extremely valuable for producing carpet, textile, cloths, all these things. Now, another example is the polyester. This is the Decaron. Now, Decaron is the material used to wrap the cushions to create the sharper and fulfilled appearance. And polyamides, this is the nylon 66. The polyamide nylon 66, Kevlar, Nomex, these are also the very important commercially available polymers. Epoxy, the step growth polymerization is also used for synthesizing a class of adhesive and amorphous solids, and they are called the epoxy. This is the epoxy resins, you see. Now, let us talk about the characteristics of step growth polymerization. The equilibrium functional group, because we are discussing the reaction engineering, so the formation of the equilibrium functional group is very important. So, functional group, this equilibrium functional group concentrations are affected by the concentration of eliminated compound. Another more important aspect is the removing of byproducts from the reaction medium reduces its concentration and thereby reducing the rate of reverse reaction and therefore promoting the use of functional group and the production of high density polymer. Now, there are several reactors of polycondensation, that the large surface area that is used for the condensation byproduct from the polymer phase. In some process, high vacuum, this may also be applied. Polycondensation, this can be carried out with the help of several polymerization techniques like melt polymerization, solution polymerization, interfacial polymerization, emulsion polymerization, solid state polymerizations. So, let us talk one by one. Melt polymerization. In melt polycondensation, a step growth reaction, this occurs in homogeneous molten polymer at a temperature above the melting point of the polymer. So, it is in the molten stage. The polymer products obtained by the melt polymerization are generally pure except for additives or other pigments added to change the appearance or extent of the life of the polymer. Now, solution polymerization. This process is mostly used when keeping the reactant within the same phase, which is very difficult while using the bulk polymerization, or when the melting point of a resulting polymer is just too high. Lower viscosity, sometimes this enables efficient heat transfer in solution polycondensation when if we compare with the melt polymerization. The interfacial polycondensation is the formation of the polymer that take place in the interface of two immiscible liquids. So, the polymer like polyurethanes, phenol formaldehyde polymers, polycarbonate, these can be prepared using the interfacial polycondensation. Emulsion polymerization or emulsion polycondensation. Usually, the polymer formation reaction occurs in a bulk of one of the liquid phase. Irreversible exothermic polycondensation involve the formation of a side product. This utilize this polycondensation technique. Solid state polycondensation. This is also known as the solid state polycondensation, which is used as a final stage of industrial processes, and this produces a very high molecular weight polymer. Pellets, like in the solid state reactor, they are held at a temperature above the glass transition temperature, but below the melting point usually occurs. Now, if the polymer that makes the functional group and functional end group mobile to react. Now, since we are here for the discussion of the reaction engineering aspect of the polymerization, then what is the basis for the analysis of polymerization kinetics? The kinetic of a reaction of or of interest from practical as well as the theoretical viewpoint. The difference between the step and chain polymerization, this resides in their respective kinetic features. Now, if we look from the theoretical viewpoint, For the practical synthesis of high molecular weight polymers, this requires the understanding of the kinetics of the polymerization reaction. Now, there is a relatively slow increase in molecular weight of a polymer in step polymerization. For example, let us take the synthesis of polyester from diol and a diacid. Now, reaction of diol and diacid monomer into form the dimer. So, this is OHR plus. This can be represented like this. Now, another reaction, that is a dimer, that then formed trimer by the reaction with diol, and this can be plus H2O. Now, the dimer then formed trimer by the reaction with the diacid monomer. This can be represented as HOROCO COOH. This is HOOC. Now, the polymerization, as the polymerization proceeds in a stepwise fashion with the molecular weight of the polymer increasing with over the period of time. So, the monomer in the reaction, this disappear far before the formation of any significant high molecular weight polymer. The rate of step polymerization process is usually therefore the sum of all the reactions of molecule of various sizes. Now, general reaction equation, this can be represented as nmer plus mr, that is n plus mr. At any time during the reaction, like HO containing molecule may react with the COH containing molecules, and this is a general characteristics of step polymerization. Now, usually when talk about the experimental evidence, the reaction rate constant for several polymerization, they are seen in the independent of the reaction time or polymer molecular weight, thus justifying the above mentioned assumption what we have discussed earlier. Now, studies of reaction of certain non-polymeric molecules come in handy to examine the polymerization kinetics. Now, let us consider the esterification of the homologous carboxylic acid. Now, here we see that the homologous molecular size can be represented, and the reaction rate constant and all those things. So, we can see that although there is a decrease in the reactivity with increase in the molecular size, the effect is significant only at a very small size. Now, the reaction rate constant, they very quickly reaches a limiting value and remains constant and independent of molecular size. Some sort of results found by for the polyesterification of sebacoyl chloride with the alpha omega alkane diols, and the thought that reactivity decreases with increase in the molecular size is just a misconception. The difficult solubility of high molecular weight molecules in homogeneous series is a pitfall which is to be avoided. Now, the kinetics of step growth polymerization, it is imperative to understand how reaction proceeds over time. Now, this information can tell us about the time it takes for a polymer to reach an optimum length. Let us consider the polyesterification of a diacid and a diol to illustrate the general form of the kinetics of a typical step polymerization process. Now, simple esterification is a well-known acid catalyzed reaction, and polyesterification follows the same occurs. Now, the reaction involves the protonation of a carboxylic acid followed by the reaction of the protonated species 1 with the alcohol to yield the ester. Now here you see that we are going to discuss the reaction mechanism. Plus Ha this is the first one, and then this further reacts with so the chain formation takes place, and this is given by like this. Plus H2 plus this is our equation 3. Now, if from this reaction all acid or alcohol species, that is monomer or dimer, up to say NMR, the reaction mixture is indicated by 1 or 2, like here we discussed. Now, since polymerization often take place in organic media of low polarity species 1 and 2, they are shown in the form of their associated ion pairs. Now, A negative is counter ion derived from the acid HA here. This is the A negative. Now, polyesterification reactions are equilibrium reaction, and considering the practical viewpoint to obtain the high yields of high molecular weight product, such polymerization are usually run in a manner so as to continuously shift the equilibrium in the direction of the polymer. Now, the rate of step polymerization, this can be conventionally expressed in terms of the concentration of the reacting functional groups. Therefore, the polyesterification can be experimentally followed by the titrating the unreacted carboxylic group with a base. Therefore, the rate of polymerization, that is Rp, this can now be expressed as a rate of disappearance of carboxylic group, that is minus dCOH over dt over the period of time t. For usual polyesterification, the polymerization rate is synonymous with the rate of formation of species 2, and that is K4. This is vanishingly small since the reaction is run under the condition that derived. So, equation 2 here and 3 towards the right, and K1, K2 and K5 are large compared to K3. So, the rate of polymerization reaction is given by Rp is equal to minus D, because it is being consumed over the period of time. This is equal to K3 C ion OH2 OH, and this is equation number 4. Now, here this is the concentration COH, OH, and this one represents the concentration of carboxylic, hydroxyl and protonated carboxylic group respectively. The concentration terms are in unit of moles of the particular functional group per liter of solution. Now, this particular equation is inconvenient as the concentration of protonated carboxylic group is not easily determined experimentally. So one can obtain more convenient expression for this Rp by substituting this group from this equilibrium expression for a protonation reaction. Now let us talk about this equation K1 over K2. This is equal to concentration of C ion plus OH. This is our equation number 5. Now if we combine the equation 4 and equation 5, then we get this dt K3 K, and this is equation number 6. Now in step growth polymerization, it is common to use this P symbol per, rather than X to refer the conversion of limiting functional groups. Now as as the conversion is equal to the probability that the particular functional group, say that is OH group, in the original reaction mixture has reacted with another functional group, say this COOH group. Therefore, the probability that a random molecule will have the length, say n, which is given by Pn is equal to P to the power n minus 1, 1 minus P, which is represented as equation number 7. So, the consumption of exactly n monomer to form this polymer chain requires n minus 1 independent chain linking reaction, each with the probability P and also that one hydroxyl group, and that is one at the end of the resulting molecule has not been consumed, which has the probability of 1 minus P. So this distribution equation is called the most probable distribution, or MPD, or Schulz-Flory distribution. Now as the conversion is equal to the probability, and a particular functional group like OH group in the original reaction mixture has reacted with another functional group like COOH. Therefore, the probability that a random molecule will have a chain length n is given by Pn is equal to P to the power n into 1 minus P. Now, consumption of n monomer to form the polymer chain requires n minus 1 independent chain linking, and each with the probability of a P. So, this Pn corresponds to the mole fraction of n-mer. Now, as conversion increases, that is P tends to 1, the mole fraction of a small molecule decreases and mole fraction of large molecule increases. But the species with the largest concentration is always the monomer, so that the chain length distribution, or equation 7, is a decreasing function of chain length. So, if you use the equation 7 to develop an expression for the weight, say CLD, this is the AB polymeric system. Now, let n be the total number of molecules remaining in the conversion and n naught be the initial number of monomer molecules. Then n is equal to n naught into 1 minus P. It is quite obvious. So, the mole fraction of n-mer is xn is equal to nn over n naught 1 minus P, and this is our equation number 8. Now, since xn is equal to Pn, or Pn to the power Pn minus 1, 1 minus P, the number of moles of n-mers are nn is equal to n naught Pn minus 1 into 1 minus P square. This is equation number 9. So, the weight fraction of n-mer is Wn is equal to nn Nwm over n naught Wm, and n naught into 1 minus P square Pn minus 1 n over n naught, which is equal to 1 minus P square P n minus 1 n. This is equation number 10, where Wm, this is the molecular weight of a repeat unit. Now, let us talk about one assumption, that is the total mass of the repeat unit in the polymer chain is large compared to the mass of end group. So, the number average degree of polymerization dP, this can be written as dP is equal to summation n is equal to 1 to infinity n into n, and that is equal to infinity 1 minus p n p to the power n minus 1 into 1 minus p 1 plus 2p plus 3p square plus and so on, and this is equal to 1 minus p over into 1 minus p over 1 minus p. This is equation, let us say 11a. Now if we slightly modify this particular equation, this becomes the dpw summation n with respect to weight. This will become summation n is equal to 1 to infinity 1 minus p square n square p n minus 1, and this is equal to 1 minus p square into 1 plus 2 square p plus 3 square p plus and so on, and that is equal to 1 plus p 1 minus p. This is, let us say, equation 11b. Now the polydispersity index, this can be written as PDI is equal to dPW over dPn, which is equal to 1 plus p. Since p is very close to 1 for a linear step growth polymerization, the polydispersity is very close to 2. So if we consider these equation 11a and equation 11b, this indicate the simple step growth polymerization, and the molecular weight averages can be calculated easily from the conversion, and that the conversion p must be very close to 1.0 to obtain the high molecular weight polymer. So, dear friends, in this particular lecture, we discussed the kinetic aspects of chain growth and step growth polymerization. We discussed about the basic nitty-gritty of the chain growth and step growth polymerization, apart from the differentiation, and we start the discussion about the kinetics of various polymerization steps. For your convenience, we have enlisted different references which you can utilize over the period of time when as and when required. Thank you very much.